Hello and welcome. Thank you for watching this video. In the previous video, we saw introduction to Azure Cosmos DB. If you have not seen it and you are new to Cosmos, then go ahead and watch it before continuing with this video. In this video, we will talk about the consistency levels in Cosmos DB and how Cosmos provides us spectrum of consistency levels option instead of choosing the binary options. So this helps us achieving trade-off between different parameters in Azure Cosmos DB. So we discussed in the last video about the Cosmos and how it is globally distributed, which helps us achieving low latency and high availability. So you can place your database in any part of the world by deploying databases in all available regions as applicable to your applications and the users. By placing this database near to the users, you achieve the low latency. So as shown here, you can see databases available in three regions: West US, North Europe, Southeast Asia. So you might enable multiple regions for write capabilities or the single one as well. So Azure takes care of replicating data in all the available regions so that the data is in sync all across the world. Hence, it provides a single image of the database or containers that you can use. With the Azure Cosmos DB, you can actually add or remove regions with just few clicks, and you don't even need to, pause your application for that. The database is highly available all the time because of home APIs that are available for the Azure Cosmos DB. So we know data is globally distributed and is highly available, but even if Azure take care of the replication of data behind the scene asynchronously, you need to specify something that tells Azure how to replicate it. What is important to you and what is your priority between high availability and the performance. So it is known as the consistency level. So by using consistency level, you are telling Azure what is important to you. So let's take example. You have multiple regions enabled and you have the data present in region A, B and C. Now suppose the users present in region A is actually writing data. It is actually updating the data, and at the same time the users present in region A, B and C are reading the data. So you need to have the strategy to replicate the data, right? Because that updated data should be available to the users present in region B and the region C. But it needs some time to replicate that data from region A to region B and to region C. So that is known as the replication of data. But it is done automatically, but you need to specify some configuration that is known as the consistency level. So that tells you how your strategy is to replicate the data. So there are basically two options that you can choose from: whether you need high availability or you need high performance, you need the consistency. So based on that, you have multiple options for the consistency levels that defines your strategy. So uh, it is not the binary value as such. So Azure provides you the spectrum of values. So consistency level gives you the spectrum of values for the replication strategy. So you can choose one that best fit your need. So each level provides availability and performance trade-off and are backed by service level agreement. So as shown here, you can see that there are multiple options for the consistency level, such as the strong consistency level, bounded staleness session, consistent prefix and eventual. So these levels are region agnostic, and that is, they are irrespective of regions. This will guarantee for all the operations specified by you from one of the consistency levels. So when you have multiple write regions enabled, and if you decide to add or remove regions, then your application does not need to be redeployed, as the home API take care of the same. And only thing you need is you need to provide the current location and multi-region enable true. So Azure will take care of the finding closest region for the same, and you have this SDKs available such as this one. So here if you see, you have set the current location as west US2 and you have enabled multiple write locations to true. So by using this, even if you add tens of another regions for your application, you don't need to stop your application or redeploy your applications, because this API, this SDKs will take care of that thing. And whatever closest region is for this west US2, so it will get the data from that particular location, so it will take care of that particular thing. So that is these are the home APIs that are available, which helps you achieve that one. So most commercially available distributed databases ask developer to choose between two extreme consistency models. So that is either the strong consistency or the eventual consistency. But whereas Azure Cosmos DB gives you spectrum of consistency levels, where you have five available options to choose from, such as strong, bounded staleness, station, consistent prefix, and the eventual. So as shown here, in the left extreme, you get the strongest consistency, but you will have to compromise for the availability and the performance. In the right extreme side, you get the weakest consistency, but you get higher performance. So that's how the spectrum goes between highest consistency and the highest performance. So the first option, or the first consistency levels in the spectrum, is a strong consistency. So the strongest consistency offers the linearizability. That means it serves the request concurrently. The reads from any available region guarantees the most recent committed version of an item. That means you will never ever get the value which is partially committed. So you will always get the value which is committed in all of the available regions. So let's take an example that you have applications where you have hosted the application database in three parts of the world: West US2, East US2, and the Central India. So time basically indicates the timeline, how the data is behaving as for the strong consistency. And you have the databases where West US2 acts as a database where we are actually committing the changes, writing the data, and East US2 Central India acts as a database where we are actually reading the data for that particular item. So on a particular given time t1, let's say we have an item where value is a, and now the West US2 and East US2 and the Central India reads the data as A at point T1. Now at point T2, let's say the user goes ahead and update the data as B. So now the data is changed in the region West US2. But now the same region West US2, if the user is reading, he also gets the data as A. East US2 and the Central India users also get the data as A. Also, now on time t3, let's consider that the data is still B and all the available regions are reading it as A. This is because we have not yet committed the data into the database and the transaction is not yet complete. So that's why we still have the data A as read from all the available regions. So these are the very small fraction of time that you can consider. That's why we still not have yet committed the data. So this is the strong consistency. Let's assume that after T3, the database synchronization happens. The data is getting committed to the database, and parallelly it is getting synchronized with the West US2, East US2, and the Central India. So that is happening. So now after the synchronization happens, let's see what happens. So West US2 gets the data as being. You can see that the user reading from the West US2 gets the data as B. East US2 gets the data as B, and also the Central India users are getting the value as B. So this is the strongest form of the consistency, where you have seen that unless and until Cosmos commits the transaction, the region, irrespective of the regions, you will not get that updated version. So you can see, even if you had written the data as B in West US2, but the other users who are reading from the West US2 only, they are also not getting the data as B. They are also getting the data as A. But once the synchronization happens, or you can say the transaction is completed, at T4 you are getting the B in all of the available region. So on a given point of time, that is T4. So that is how the strongest consistency behaves. So this is more suitable where you need most recent committed version of the data with the strong consistency where partial write will not work. So here you will get the less performance as compared to the other consistency level, but what you prioritize is the consistency in the data. So example is basically any financial institute, banking institute. So in that case you can compromise on the performance a little bit, but you need the most recent committed version in all of the available regions. So that's the best example for this kind of consistency. So now this next option we have is bounded staleness. So in this case read might lag behind writes by at most k version of an item or time interval t, so whichever reaches first. So in this case it means that you will have to choose bounded staleness with some configuration, that is staleness can be configured in couple of ways, either the number of versions of an item or time t by which the reads might lag behind. So you can provide couple of options. So it's okay that my data gets updated by k or k number of versions, so that is allowed, but also let's say 5 seconds, after 5 seconds it's okay for me to replicate the data. So these are the configuration that you need to provide if you choose for the bounded staleness. So let's take similar example where we have applications where we have multiple regions where we have deployed our database, and we are considering the similar timeline and what happens if you write the data. So we have three databases that are present, so we are considering West US2 as the region where we are actually writing the data in this example. So on a given time t1, let's say we have a data A for an item, and the West US2, East US2 and the Central India is reading the data as A. On a given time t2, let's assume that the user go ahead and update the data as B for that particular item, and now we are reading data in all of the regions as A. Just assume that we have not yet committed the data in the database as of now in T2. Now at point T3, the data gets committed into the database, but that is only specific to the West US2. So here that's why West US2 reads the data as B, but rest of the regions are reading data as A. So this is like a difference between the bounded staleness and the strong consistency. So in the strong consistency, irrespective of the region that is present, it's either yes or either no. So it will be actually committed in all of the regions or it will not be committed. So that's in the case of strong consistency, but in case of bounded staleness, you are first committing the data into the current location, so which is a West US2, and once that is done, then based on the configuration that you have provided, let's assume that after 5 seconds, so the synchronization will happen. So now the data read in the West US2 is B, but not in case of others. So after that configured time is elapsed, so after that let's say synchronization happens. So let's say the data gets updated in the East US2 and the Central India as well. So after that happens, so it will available in all of the region. So that is a difference between the strong consistency and the bounded staleness. So this is to be chosen in a global distributed application that expects low write latencies but also requires global order guarantee. So you can see that the order in this case is guaranteed to be in the way it is updated. So it's not like an order kind of a data. So it will always be order, but you will lag behind by some time. So that is the difference. So but the best example for this kind of bounded staleness you can use is it is great for the applications featuring group collaborations and the sharing, or publisher subscriber model or the queuing model. So in that case you can use bounded staleness where you need it's okay to have that gap in between, lag in between the updates in multiple regions, but the order is important too. So that is bounded staleness. So the next consistency session. So in this case, the data gets updated and it is available for read only to that particular session before you actually replicate the data. So when you update the data, it will only be available to that particular session, whether it is present in one region or multiple region, but this is very much specific to the session. So we saw in the bounded staleness that the data gets updated and it is straight away available to that particular location, and after that it gives priority to other regions. But in case of session, it is not specific to the region, but it is specific to the session of the user. So in this case, within a single client session, reads are guaranteed to honor the consistent prefix. Monotonic reads, monotonic writes, read your writes, and write follows the read. So these are all things that are guaranteed in this session. So it is very much specific in a case where you have an application which is in a context of the user. So if I am doing something, so the data is very specific to that particular user. So it assumes that you will have only single writer session, and if in case you have a situation where the session can be shared, so you might have multiple writers in that case. So to achieve the session consistency, you need to share the session token with all of the users, whether they are present in a single region or multiple region, but you need to have the same session token with that user as well. So consider the similar example. We have an application where we have hosted the databases in multiple regions, and we are considering the timeline, how the data behaves with respect to the time, and we have the data present in the say East US2, West India, and West US2. So we are considering that we are writing data in the West US2 under the session 1. So let's say at point T1 we have data present in an item which is A, and now all of the regions are reading the data as A irrespective of the session. But now at time T2, a user using the session 1 is updating the data as B. Now the same user is reading the data as A in case of West US2 and also in case of the other regions, because right now the data is not yet committed into the local database copy. Now at point T3, what happens is the data is committed in the West US2. So you can see that the data is available for that particular session specific user. So whether it is in West US2 or East US2, so it doesn't matter. So East US2 is also getting the data as B. But in case of session 3, the data is still A because the synchronization or the replication of data across the region has not yet completed. It is just that you have committed the local copy of that particular data for that session. Now let's assume that synchronization happens and your data gets replicated in the West US2, East US2, and the West India. That means the data is now in sync for all of the regions. So at T4, the item value which is seen by all of the session is B. So that is a session. So it is a very much specific to the user context, and if you have such a scenario, it is better to use the session consistency. And this particular session consistency is widely used consistency level, and it provides the right latencies, availability, and read throughput, and comparable to that of the eventual consistency. But it also provides the consistency guarantees that suits the need of application written to operate in the context of the user. So the best example for this is nothing but the user shopping cart. So shopping cart is very much specific to that user. So this is very uh, good example for this session consistency level. So in such scenarios you can use the session consistency level, but in case of banking or any financial institute, it does not make sense to use the session as the consistency level. So now if you observe, we are actually moving from left to right in the consistency spectrum. So as we move from left to right, the consistency is getting weaker, but the performance is increased as we move from left to right. So we first saw the strong, which was the strongest consistency, but you have to compromise on the little bit performance as well. But in case of eventual, it is the weakest consistency. But if you will get the data faster from the database. So that is the difference. So now we are at a stage where we are looking at consistent prefix. So the consistent prefix actually guarantees that the updates returned contain some prefix of all the updates with no gaps. So there will not be any gap when you read the data. It makes sure that the reads are never out of order writes. So if writes are performed in the specific order, which let's say A, B, C, then client will see the data as A, or data as AB, or data as A, B, C, but you will never see AC, ACB, or CB, etc. So it will guarantee that the order is maintained the way it was updated in that particular database location. So let's consider the similar example. We have similar kind of situation and we are considering the timeline, and let's assume that at point t1 we have data A present in west us2, and let's see how the data is getting read. At point t2 the user is updating data from A to B. At point t3 it updates data as B to C. Now let's see how it behaves. So if you see here, the data may not be read in a um, consistent manner here. Let's say West US2 is reading data as A at point T2, but Central India is reading it very faster and it is getting the update as B. But at point T3, the data read by West US2 is B, and at point T3 the East US2 is still reading the data as A. It still not have got the update for the B, and Central India is reading the data as B at point T3. So now at point T4, let's see what happens. So if you see, the data may not be consistent across the region, but only important aspect of consistent prefix is that the order is maintained. So if you see, you will get the better performance of reading the data, but it will also maintain the order. So the important factor in consistent prefix is the order. The order in which the data was updated at West US2 was A, B, C, and if you observe, the West US2, East US2, and the Central India, all of the regions are reading the data as A, B, and then C. So that is the consistent prefix. It provides the write latencies, availability, and read throughput comparable to the eventual in the rightmost, but also provides order guarantees. So that suits the need of scenarios where order is important. So the next and the last consistency level that we have in the spectrum is nothing but the eventual consistency. So you will get the weakest consistency, but you will get the best performance in the all of the 5 consistency levels. So let's consider the similar scenario, and we are now at point T1 where the data is A and it is getting updated at T2, which is B. At T3 we have the data updated as C. Similarly, the data gets updated in the West US2, and now the data is how the data is getting read in West US2 is something different. So that's how the data gets updated and the read from West US2. So the eventual form of consistency does not guarantee that it will be in a sync or it will be in a order of the way it was updated in the writer. So let's say West US2 at point T3, till the point T3 it read the data as A, but at T4 it read the data as C, but after C it got the update of B, and then it got the update of D, and now after that at T7 it is getting F as the data. So the order here is not guaranteed. You are getting the data as A, C, B, D, F, but the data actually updated was in order which was A, B, C, D, E, and F. Similarly, East US2 and the Central India, the data will not be guaranteed to be in order. So let's see. So that's how the data gets read between the different kinds of regions. So here the important factor is basically the data may not be in order, but you will get the data faster as compared to other all of the available consistency levels. So that's how the eventual consistency is basically. So the best example for the eventual consistency is basically whenever you need a faster performance and where the order of the data does not matter. So the best example for eventual consistency is the number of retweets in the Twitter. So that is the example. So the order is not important here. What you care about is the count of retweets. So that is the example of eventual. So that's all about the consistency level in Cosmos DB, and I hope now we are aware of what is the best consistency level for particular situation, considering the different spectrum of the levels that we have in Cosmos DB. Thank you.